Welcome to the Stratix 10 HyperFlex Architecture Overview online training. My name is Marlon Price and I will be the presenter for this training. During the presentation, you may pause, stop, and start the training at any time. On the left side of the window, you will find the Menu tab, which allows you to skip forwards or backwards to specific slides. There you will also find the Notes tab, so you can follow along by reading a script of the course if you find that helpful. By the end of this course, you will have an understanding of the brand new features that make up the HyperFlex architecture found in Stratix 10 FPGAs, and you will understand how these features will allow your designs to achieve clock speeds of up to 2 times over the clock performance possible in prior FPGA architectures. We will begin this training describing the new HyperFlex architecture and its advantages. Then we will address a few questions that commonly arise after learning of this new architecture. Lastly, we will do a brief overview of how designs can be optimized to take advantage of this architecture. More details on this optimization flow will be covered in additional online training similar to this one. So let's begin with a look at the new HyperFlex architecture. Stratix 10 FPGAs and SoCs deliver capabilities that were previously unimaginable from a PLD or programmable logic device. When compared to previous generation high-end devices, Stratix 10 delivers twice the core performance, up to 70% lower power, over 4 times the logic density, and additionally, on SoC devices, an integrated quad-core 64-bit ARM Cortex A53 hard processor system. These breakthroughs in performance and capability are enabled by the two exciting new developments that you see here. The Intel 14nm Tri-Gate process technology that will be used to fabricate these devices, and the all-new HyperFlex Core Fabric architecture. Before we get into the specifics, you may be thinking, is a new programmable core fabric architecture even necessary? What's the big deal? Well, next-generation systems targeting FPGAs require ever-increasing performance and throughput, and the reality is that today's FPGA architectures do not hold up well against these demands. One technique that has been used in the past to increase throughput is to make on-chip buses increasingly wider, to the point where it is now common to see 512-bit or 1024-bit wide buses in an FPGA design. However, increasing bus width makes it more costly to implement logic functions across each bit of the bus, such as comparators or checksums. Simply making buses wider is not sufficient. We need to do more. Another consideration is that as device geometries continue to shrink with each process node, the interconnect delays between the logic cells and the core fabric are dominating the total delay. So simply evolving the existing architecture into the next process technology node does not address this growing concern. As a result, to address these performance limitation issues, Altera thought out of the box and came up with what is being called the HyperFlex Core architecture. Although this is a new innovation, it is based on concepts of which you are already familiar, namely retiming, pipelining, and loop optimization. While these concepts can be done in any existing FPGA architecture today, the innovative approach that Altera has taken with the HyperFlex architecture is a big improvement that leads to unimaginable levels of performance simply not possible with a conventional FPGA architecture. Traditional FPGA architectures are already register heavy. There are multiple registers in every logic cell, as well as registers in I/O, multiplier blocks, memory blocks, and dedicated hard IP like transceivers. This is a conceptual diagram showing a conventional FPGA architecture without hyperregisters. The FPGA structure is mostly made up of logic cells that are used to implement general logic functionality. In ARIA and Stratix series devices, the logic cells are called ALMs, or adaptive logic modules. To connect the output of one ALM to the input of another ALM in another area of the device, the signal would have to go through multiple row and column resources as shown here. Though I am only showing ALMs here, all device structures, including multiplier and memory blocks, would be connected using this same strategy. If a pipeline register stage is to be inserted in the path between the two ALMs, then the signal path between them must take a detour through an additional ALM in order to make use of that ALM's register. Unfortunately, there is an expense to using an ALM register for pipelining in the form of a significant increase in the delay of the timing path. Now, the actual delay incurred depends on the particular target device, but in general, each time the signal leaves a row and column resource to go into an ALM, it encounters additional delay from the local routing needed to feed the ALM itself as the signal passes around the lookup table or LUT, and the local routing to exit the ALM back to row and column resources. As a result, these delays have the effect of limiting how many actual pipeline stages can be inserted in the path before no more clock performance improvement is gained. Traditional FPGA architectures are already register heavy, but the HyperFlex architecture takes this further by introducing even more registers throughout the core fabric. The key building blocks for the HyperFlex architecture are bypassable hyperregisters located in every routing segment and at all block inputs in the core. Unlike existing architectures, this is a more fine-grained approach because there are really hyperregisters located everywhere throughout the core fabric. This means your design has many more options for inserting register stages than before. As a result of this fine-grained approach, the HyperFlex architecture enables three key performance improvement strategies, which are hyper-retiming, hyper-pipelining, and hyper-optimization. The HyperFlex architecture addresses these issues by providing registers everywhere. There are bypassable hyperregisters in the routing muxes. This means that as a signal moves between any row and column resources, there is an option to register or not register that signal. There are bypassable hyperregisters on the inputs to all block structures. For example, ALM lookup tables, ALM registers, multiplier blocks, and memory blocks. And all of the individual ALM registers are bypassable. This means that instead of registering a signal in an ALM, that registering can be done downstream at a more ideal hyperregister location for timing. But the ALM's control signals could still be used by that downstream hyperregister. You can see more on the impact of this architectural feature in follow-up online training. Here is a representation of the HyperFlex FPGA architecture showing the HyperFlex registers as the orange squares. As you can see, the HyperFlex architecture provides an abundance of hyperregisters located conveniently around the device to maximize design performance. In fact, with the HyperFlex architecture, there are over 10 times the number of hyperregisters as there are in conventional ALM registers. Thus, to follow the same path as we showed before from one ALM to another ALM, the signal path has a huge number of locations in which it can pass through a hyperregister. Let's follow the same path as before. Now let's follow another path. In both paths, and any other path you may draw between the two ALMs, choosing a register location for a pipeline stage is much simpler than before. So as a result, pipeline stages can be added virtually anywhere between two logic structures. And this can be done without incurring the timing delay of using a register in an ALM to do the same thing. In effect, registers become cheap as the cost to adding them to a signal path has been eliminated by the architecture. This brings up some common questions on the architecture regarding power, hold times, and clocking. Let's address those now. With the addition of all the hyperregisters to the architecture, how does that affect power? Well, the hyperregisters are simple D flip-flops. so each requires only a few transistors to implement. This is less than the number of transistors required to implement an ALM register with its flexible control signals, much less than the number of registers required to implement more complex blocks like the RAM and DSP blocks, and significantly less than the number needed to build transceivers or hard memory controllers. As a result, the hyperregisters collectively contribute minimally to the total static power, less than 1%. With regards to dynamic power, hyperregisters on their own do not cause an increase in power. This is because during optimization, the software tools take register stages implemented in ALM registers and replace them with hyperregisters. Overall, this proves to be more efficient than using other ALM registers for the same type of optimization. Keep in mind, though, that since the hyperregisters do enable designs to run faster, increasing the clock speed of your design will cause the dynamic power consumption to scale with that frequency increase. Countering the potential power increase due to running designs at higher frequencies, the Intel Stratix 10 device family is built on the Intel 14nm process, which provides significant power savings. With this in mind, it is expected designers will see a power parity running their higher frequency designs when compared to their implementation on previous generation FPGA families. With traditional FPGA architectures, registers are designed for no hold time issues, assuming dedicated clock trees are used correctly. But with all these hyperregisters everywhere, aren't hold times going to become a problem? Well, with this increase in speed comes a location rule. You cannot enable adjacent hyperregisters everywhere in the device. So looking at the example diagram here, we cannot enable all three hyperregisters to connect these 4 row channels in series. Now the exact number of adjacent registers that cannot be enabled depends on the specific routing resource being used. For the shortest routing channels, the restriction may mean 2 or 3 adjacent registers. For the longest routing channels, there would be no restriction at all. To understand this, you must first consider why there are so many hyperregisters in the first place. The point is not so a user can enable all of them at once. The point is so the compiler has lots of options for placing a pipeline register. So the compiler can really choose the ideal location for that register with respect to timing. And since the Quartus 2 compiler is aware of this location placement restriction, it will ensure adjacent hyperregisters are never enabled. So if you are a user, you don't have to worry about this rule at all. It's taken care of for you. The location rule ensures that hold time margins are met between hyperregisters. And since the maximum clock speed of the Stratix 10 device family is 1 GHz, there are not many reasons to make it necessary to enable all adjacent hyperregisters. But these situations can arise. What I mean is that there are certain situations where the compiler wants to enable a hyperregister, but it cannot due to this location rule. If this occurs, it is reported in the Fast Forward Compile report. This report and what to do when a situation like this arises is discussed in follow-up online training. The last questions have to do with clocking. Will the traditional FPGA clock tree support all of these registers? Did Altera have to expand the clock tree to do so? With the new HyperFlex architecture comes a new synthesizable and programmable clock tree. This clock tree is synthesized locally during compilation to build a tree only where it is needed. This provides less variability and lower clock skew over a traditional global clock tree, enabling clock rates up to 1 GHz. The new clock tree is also more flexible. Instead of a clock tree pre-built in silicon, the clock tree is more similar to the row and column resources in that there are dedicated clock routing segments throughout the device that can be stitched together to create a clock region. The result is that you can have a greater number of clock regions than before and up to 32 independent clocks in one section of the chip. Because the new clocking structure allows for smaller and more focused clock regions, you can have lower clock tree power dissipation due to less switching capacitance and branch disabling. I'll show an example of this in the next two slides. And the clock tree is backwards compatible, so if needed, the clock tree can be synthesized into true global, half-chip, and quadrant clocks to which FPGA designers are familiar. Also, though our architecture diagrams show the routing channels between the ALMs, the physical FPGA is made up of layers in silicon. So rather than the routing channels being between ALMs, the routing channels, including the clocks, actually run over top of the ALMs as well as the hyperregisters. So it was not necessary to expand the clock tree to connect to these additional hyperregisters. Let's do a quick comparison of conventional clocking versus the new synthesizable clock tree. With the conventional FPGA, the clock tree is divided into global clocks that drive all areas of the chip and regional clocks that reach a quadrant of the device. If a logic cloud straddles two quadrants like pictured here, this would require enabling a global clock. Note this could also be done with the dual regional clock, which makes use of two adjacent regional clocks. If the fitter chooses to place logic running off of a second clock into two discrete areas of the FPGA, like shown here, the only way to reach both areas would be to enable a second global clock tree. And finally, another logic module running off of a third clock is placed in one quadrant of the chip. To reach these registers, a regional or quadrant clock could be enabled. But notice in each case, there are large sections of the FPGA where the clock resource is enabled, but in which no logic is actually running off of that clock. Since the entire clock tree is enabled, this translates to additional power consumption for the device. Now, let's look at the programmable clock tree synthesis of Stratix 10 devices. This clock tree is composed of segments that span the FPGA's XY coordinate system, creating clocking sectors. The clock tree is only synthesized to the sectors where the clock is needed to drive logic placed in that sector. For clocking of the first module, instead of using an entire global or two regional clocks, the clock tree segments are synthesized to encompass only the area needed for that module. Again, for the second module, the clock tree can be synthesized to drive only the necessary logic. Even though the fitter may rarely, if ever, split a clock domain in this way, it is still not a problem to synthesize the clock tree as needed to drive just those registers. And finally, for the last logic cloud, instead of using an entire quadrant clock as before, the clock tree is synthesized to a region even smaller than a quadrant. In all cases, there are not any unused parts of the clock tree or sectors consuming extra power. Now that I've covered all of the architectural information, I will talk about how you can target Stratix 10 with your design flow. To extract the most benefit from the HyperFlex architecture, Intel FPGA has defined a three-step process you can follow consisting of hyper-retiming, hyper-pipelining, and hyper-optimization. Depending on how your design is coded or structured, significant performance improvement is possible in any of the steps. But in general, as you move from one step to the next, the performance of your design grows as well as the design effort to implement that step. The three steps are hyper-retiming, hyper-pipelining, and hyper-optimization. The first two stages are based on well-understood design techniques used commonly by design engineers today to improve performance. Many times, they account for most of the performance gain in the three-step process, so some designers can stop after hyper-retiming or hyper-pipelining. But in cases where a designer wants to achieve even higher clock speeds, then the designer can move on to the final stage, hyper-optimization. This stage may require dramatic restructuring of the design based entirely on its functionality and how the original RTL is coded. It's important to remember that you as a designer can choose whether to implement these techniques selectively or globally depending on your design and your performance goals. Though retiming, pipelining, and more advanced optimization will see performance gains when used on any FPGA today, their results when used on the HyperFlex architecture is much greater. Again, the HyperFlex architecture was designed with these optimizations in mind. Now I want to go over the basics of design for the HyperFlex architecture. Stage 1 is Hyper-Retiming. Hyper-Retiming involves moving existing registers in your design from ALM locations into hyper registers to cut critical paths and improve overall performance. In some cases, due to the architecture of hyperregisters, it may not be possible to move the ALM registers into them. So hyper-retiming may also involve removing any restrictions that would prevent ALM registers from being retimed into hyperregister locations. Stage 2 is hyper-pipelining. Hyper-pipelining involves adding new registers to the design RTL so that they can then be retimed into hyperregister locations. This cuts critical paths even more as there are more overall registers in the design, so the individual register-to-register paths in your design can be lessened even more. Stage 3 is hyper-optimization. Hyper-optimization involves loop management or restructuring design loops to lessen or eliminate their negative impact on performance. Using hyper-optimization allows you to take your design beyond the effects of hyper-retiming and hyper-pipelining alone. Here are some benchmarks of 3 different customer designs that Altera compiled using the Stratix 10 design tools currently in development. The examples shown here include a communications data path design, a control logic design, and a coprocessor design. In each case, you can see that the design target was significantly faster than the baseline performance which was achieved in an FPGA with a conventional architecture. You can also see from the table 2 of the 3 designs use the full 3-step process all the way through hyper-optimization to achieve the design target and obtain 2x or more performance increase. However, you can see that the coprocessor design reached the target performance after only hyper-retiming and hyper-pipelining. In this case, the hyper-optimization step was not required. Furthermore, in the case of the control logic design, hyper-optimization was able to help this design reach a nearly 5x performance increase from the baseline to reach the design target of over 550 MHz. When I talk core performance increases in Stratix 10 devices, this offers several advantages for you and your design project. 1. Obviously, this translates into faster clock maximum frequency, or Fmax, so you can process more data and or support more features than your competition. 2. It can also be used to reduce engineering development time by making it easier to close timing. This increases designer productivity and can potentially reduce time to market. And 3. Under the category of reduced device cost, the increased performance may allow the use of a slower speed grade device, reducing the cost of the solution. Or you may decide to use the performance improvement gain to take your design running 2x faster and run it at half the original bus width to reach a performance parity, but allow for use of a smaller device and again reduce the cost of your solution. So this concludes our look at the Stratix 10 HyperFlex architecture. As you can see from this training, the hardware changes available in the HyperFlex architecture enable designs to reach up to 2 times performance gains, on average, over previous FPGA architectures. These include HyperFlex registers on routing channels, HyperFlex registers on block inputs, bypassable ALM registers, and programmable clock tree synthesis. To take advantage of the architecture, you as a designer can employ the design techniques of hyper-retiming, hyper-pipelining, and hyper-optimization. If you would like to continue in your learning of the Stratix 10 HyperFlex devices, you can view the free follow-up online training shown here. New Quartus 2 HyperFlex Tools. This online training goes into the new features found in the Quartus 2 software that take advantage of the new HyperFlex architecture. And Stratix 10 Fast Forward Compile covers how you can discover what performance gains are possible for your design targeting a Stratix 10 device without making any design modifications at all. Altera also offers 2 days of full-day instructor-led courses devoted exclusively to optimizing Stratix 10 designs. The Optimization with Stratix 10 HyperFlex Architecture class discusses the details of the HyperFlex architecture, hyper-retiming, and hyper-pipelining and gives hand-on experience through lab exercises. Advanced Optimization with Stratix 10 HyperFlex Architecture teaches techniques for optimizing loops, which are one of the roadblocks for the hyper-retimer. Again, hands-on experience through lab exercises is provided. Lastly, when you register for this training, a link was sent to you in your confirmation email that links to a short online survey. Please complete the survey to let us know what you think of this training and if you can think of ways it can be improved. This concludes this online training. Again, my name is Marlon Price, and I thank you for your time.